What happens when something truly ends? Not just a person, a star, or a civilization, but the very atoms that made them. Atoms are supposed to be the unbreakable foundation of reality, the pieces everything else is built from, but even atoms aren't forever. Under the right conditions, they decay, they break apart, and sometimes they vanish into something else entirely. Let's explore how atoms transform under extreme conditions, like in black holes or exploding stars. We'll look at how energy and mass are connected, what entropy means for the fate of matter, and whether anything ever truly ends. Anatomy of an atom. Structure and stability. At the very core of everything we see, touch, and experience lies something invisible to the eye, the atom. From the air we breathe to the stars in the sky, all matter is made up of these tiny building blocks. Small, atoms are incredibly well-organized systems, each one containing its own internal structure. An atom begins with its center, called the nucleus. This is where most of the atom's mass is located. Inside the nucleus are two types of particles, protons and neutrons. Protons carry a positive electrical charge. Neutrons, on the other hand, have no charge at all. They are electrically neutral. These particles are packed tightly together at the heart of the atom. Despite the close quarters and the positive charges that would normally repel each other, they remain bound, held together by a force stronger than the repulsion, something called the strong nuclear force. It is one of the four fundamental forces in nature, and without it, the atom would simply fall apart. Surrounding this dense core is a space where electrons move. Electrons are much lighter than protons or neutrons, and they carry a negative charge. They do not stay in one place like marbles circling a drain. Instead, they exist in a cloud of motion, moving rapidly within specific energy levels, or regions known as shells. These shells surround the nucleus at different distances. The closest shell holds the electrons with the least energy, while those further away hold electrons with more energy. Despite the constant movement, electrons remain in these shells because they are attracted to the positive charge of the nucleus. Opposites attract, and this electric pull between the negatively charged electrons and the positively charged protons keeps the atom from flying apart. The number of protons in an atom's nucleus is what defines the element. Hydrogen has just one proton. Helium has 2. Carbon has 6. This number is known as the atomic number, and it gives each element its identity. But atoms are not just about identity, they are also about balance. For an atom to be neutral, the number of protons and electrons must be equal. This means that the positive and negative charges cancel each other out, making the atom electrically neutral overall. Neutrons, though uncharged, add to the mass of the atom and play a vital role in keeping the nucleus stable. Without them, the balance of forces within the nucleus would be upset, and the atom could become unstable or fall apart. What makes this balance so interesting is that it's not always perfect. Some atoms have more or fewer neutrons than usual. These variations are known as isotopes. For example, carbon usually has 6 neutrons, but it can also have 7 or 8. These are still carbon atoms because they have 6 protons, but the extra neutrons can affect the atom's stability. Some isotopes are stable and last forever, while others are unstable and break down over time, releasing energy in the process. This process is known as radioactive decay. While the nucleus defines the atom's identity and stability, the electrons define how the atom behaves. The outermost electrons are the ones that interact with other atoms. When two atoms come close, their outer electron shells may overlap, and the electrons can be shared or transferred. This is the basis for chemical bonds, and ultimately, for the formation of molecules and matter. Even though electrons are drawn to the nucleus, they do not collapse into it. This is because they also have energy from their constant motion. It's a careful tug of war, the electric force pulling them inward and their motion pushing them outward. The result is a delicate balance, where the electrons are trapped in place around the nucleus, always moving but never falling in. This balance of forces between attraction and motion is what makes the atom such a remarkable system. The atom is not a lifeless particle. It's a system full of movement and tension, working perfectly to keep itself together. Each part plays its role. Protons set the atom's identity and contribute to its charge. Neutrons help stabilize the nucleus by adding mass without adding repulsive force. Electrons add behavior and flexibility, allowing atoms to build, connect, and change. But none of it works unless the forces are in balance. If the balance shifts, too many protons, too few neutrons, too much or too little energy, then the atom can become unstable. Yet, in the vast majority of cases, atoms do find that balance. They remain whole and stable for long periods, giving structure to everything from a grain of sand to a mountain. What seems chaotic or random on the outside is, on the atomic level, full of order and precision. Every material in the universe owes its form to this underlying structure. Mass-energy equivalence, the currency of transformation. Mass and energy may seem like two completely different things. One we feel as weight, the other we see in action, light, heat, motion. But in the world of atoms, these two are deeply connected. This idea comes from one of the most famous equations in science, E equals mc squared. It comes from Albert Einstein's theory of relativity. It says that energy and mass are not separate things. They are two sides of the same coin. E stands for energy, m stands for mass, and c is the speed of light in a vacuum. The speed of light is a huge number, about 300,000 kilometers per second. When you square that number, multiply it by itself, it becomes even more massive. This tells us something surprising. Even a small amount of mass can become a huge amount of energy if transformed completely. This principle becomes important inside the atom, especially during nuclear reactions. In most cases, atoms are stable. Their parts stay where they are. But when an atom becomes unstable, something different can happen. It may split apart or change into a different form. In the process, a small amount of the atom's mass disappears. But it is not lost. That mass becomes energy. The change is not random. It follows the rule of E equals mc squared. The exact amount of mass that disappears will match the exact amount of energy that appears based on that formula. The energy can take many forms. It may appear as heat, light, or movement. In some cases, it is released as radiation. This is why radioactive decay produces energy. It is not magic, it is math. When a radioactive atom breaks down, it often turns into a different kind of atom. This transformation is called nuclear decay. The nucleus may lose a proton or a neutron, or it may split into smaller parts. When this happens, the new atom has slightly less mass than the one it came from. The missing mass becomes energy. This process doesn't destroy the atom. It changes it. It is not destruction, but transformation. We can see this clearly in nuclear fission, the process where a large atom, like uranium-235, splits into two smaller atoms. This doesn't just break the atom into pieces, it rearranges it. During this process, a tiny fraction of the original atom's mass is converted into energy. Even though the change in mass is very small, the energy released is enormous. That's because of the speed of light squared in the equation. A small amount of mass multiplied by a huge number becomes a lot of energy. This is what powers nuclear reactors and nuclear weapons. The energy from mass, once released, can be controlled or uncontrolled, depending on how the reaction is set up. But at the center of it all is the same principle. The reverse is also true. Under the right conditions, energy can be turned into mass. In high-energy environments, such as the early universe just after the Big Bang, energy turned into particles of matter. Scientists have even done this in particle accelerators. When two high-energy photons collide with enough force, they can create matter. The energy becomes mass. This tells us something profound. Matter, as solid and permanent as it seems, is really just one form of energy. At the atomic level, everything is part of a flow. Atoms are part of a system that transforms and transfers energy constantly. Even inside a stable atom, mass and energy are always present, tied together. The strong nuclear force that binds protons and neutrons uses energy. That energy adds to the mass of the nucleus. This is called binding energy. In fact, the mass of a nucleus is slightly less than the total mass of all its protons and neutrons added together. The difference is the energy that holds them together, and it shows up as a small loss in mass. Again, the mass isn't gone. It's part of the system, held as energy within the atom. This balance between mass and energy is how stars shine. Deep in the core of a star like our Sun, atoms of hydrogen are pushed together so tightly that they fuse, forming helium. In the process, a small amount of mass is converted into energy. That energy travels through the star and eventually reaches us as sunlight. Every ray of light from the Sun is a reminder of E equals mc squared in action. This idea also helps explain why some atoms are more stable than others. The more tightly an atom's nucleus is bound, the more binding energy it has. That means the mass of the whole nucleus is lower because some of its potential mass is used up as energy to keep it stable. Less tightly bound atoms have higher total mass and may become unstable over time, breaking down and releasing that extra mass as energy. In all these cases, mass and energy shift forms, but the total remains the same. This is called conservation. The total amount of energy and mass in a system doesn't vanish, it just changes shape. The same principle applies to all atomic events. Whether an atom is breaking apart, joining with another, or simply holding together, energy and mass move together through the transformation. The many faces of radioactive decay. Radioactive decay is not one single process, but a group of many different types. Each type changes the atom in a unique way. Some change the number of particles in the nucleus. Others shift the atom's identity. Still others release energy without changing the element at all. One of the most common types is alpha decay. In this process, the nucleus of an atom gives off an alpha particle. An alpha particle is made of 2 protons and 2 neutrons, essentially the same as the nucleus of a helium atom. When an atom loses an alpha particle, it loses 2 protons. That means it becomes a completely different element, one that sits 2 places earlier on the periodic table. For example, when uranium-238 undergoes alpha decay, it becomes thorium-234. This process also reduces the mass of the atom, since 4 heavy particles have left the nucleus. The energy released is relatively high, but alpha particles don't travel very far. A sheet of paper or even the surface of human skin can stop them. Still, inside the body, they can do significant damage if inhaled or ingested. Another type is beta decay. This happens when a neutron in the nucleus turns into a proton. When that happens, the atom gives off a beta particle, an electron, and a small, nearly massless particle called an antineutrino. Since the number of protons increases by 1, the atom becomes a new element, one that is 1 step higher on the periodic table. For example, carbon-14 undergoes beta decay to become nitrogen-14. This can help an unstable atom move closer to a stable form. There is a second version of beta decay called beta plus decay, or positron emission. In this version, a proton in the nucleus turns into a neutron, and the atom releases a positron, a particle that is like an electron but with a positive charge, and a neutrino. When this happens, the atom loses a proton, which means it becomes a different element, 1 place lower on the periodic table. This process is common in atoms that have too many protons compared to neutrons. The positron doesn't last long. It quickly meets an electron, and the two destroy each other, releasing energy in the form of gamma rays. This kind of decay is used in medical imaging, such as PET scans, where positrons help create detailed pictures of the body. Then there is gamma decay. This one doesn't change the number of protons or neutrons in the nucleus. Instead, it releases extra energy stored inside the nucleus. After a nuclear reaction, or another type of decay, the nucleus may be in an excited state, like a stretched spring. Gamma decay releases that energy, usually in the form of high-energy electromagnetic radiation called gamma rays. These rays have no mass and no charge, but they carry a lot of energy and can pass through many materials, including human tissue. That's why gamma rays are dangerous and why lead shielding is used to block them. Sometimes an atom will change not by giving off a particle, but by pulling one in. This process is known as electron capture. An inner electron falls into the nucleus and combines with a proton, turning it into a neutron. The result is the same as beta plus decay. Electron capture happens in atoms with too many protons, where becoming more neutron-rich leads to a more stable form. It often leads to the emission of X-rays as the atom rearranges its remaining electrons to fill the missing space. There's also a more dramatic process called spontaneous fission. This usually happens only in very heavy atoms, like uranium or californium. In spontaneous fission, the nucleus splits into two or more smaller nuclei, along with several neutrons and a large release of energy. Unlike standard fission used in reactors, this type happens without needing to be triggered by another particle. It is a rare event, but when it happens, it changes the atom completely, leaving behind entirely new elements and a burst of energetic particles. The neutrons released can cause other nearby atoms to split, leading to a chain reaction if conditions allow. Some decay types are more exotic. One is cluster decay, where the nucleus emits a small clump of particles, heavier than an alpha particle, but lighter than fission fragments. For example, a nucleus might emit a fragment like a neon-20 nucleus. This type of decay is rare and mostly seen in very heavy elements. In double beta decay, two neutrons in the nucleus turn into two protons at the same time, releasing two beta particles and two antineutrinos. It's a very slow process, taking billions of years in some cases, but it happens in certain isotopes where regular beta decay is not possible. A special version, called neutrinoless double beta decay, has been theorized but not yet confirmed. If found, it would show that neutrinos are their own antiparticles, revealing a new layer of physics hidden in radioactive decay. The forces inside the nucleus are complex. They must balance the pull of the strong nuclear force with the push of electromagnetic repulsion. When that balance is off, the atom will find a way to adjust. Sometimes that means losing a particle. Other times it means changing the identity of a proton or neutron. And sometimes it means releasing pure energy. Beyond half-lives, rethinking atomic longevity. When we think of something breaking down, we often want to know how long it will last. For atoms that decay, the most common way to answer this is with something called a half-life. A half-life tells us how long it takes for half of a group of radioactive atoms to decay into something else. It's a simple number, and it helps us make predictions, but it doesn't tell the whole story. A half-life is not a countdown. It's not the age when an atom dies. Instead, it's a measure of probability. If you start with a pile of 1,000 atoms of a radioactive element, and the half-life is 10 years, then after 10 years, about 500 atoms will still be left. After another 10 years, about 250. But that doesn't mean each atom lasts 20 years or even 10. Some decay quickly, while others might last much longer. Some could remain unchanged for millions of years. The half-life just gives us the average behavior of a large group. When we zoom in to look at single atoms, the idea of a lifespan starts to get blurry. That's because decay doesn't follow a set schedule. There's no clock ticking inside the nucleus. Instead, each atom exists in a state where decay is always possible. It's as if the atom is constantly flipping a coin in secret. Each moment carries a small chance that the nucleus will change. And when it does, that's when the atom releases energy and transforms. But we can never say exactly when it will happen. Some atoms, like polonium-214, decay extremely fast. Its half-life is less than a second. Others, like tellurium-128, have half-lives so long they're hard to imagine, trillions of years. Yet both are governed by the same basic rules. The difference lies in how stable their nuclei are and how much energy they carry. A small change in nuclear structure can shift the decay rate by an enormous amount. That means that two very similar atoms might behave in very different ways. Scientists once thought that half-lives were fixed and could not change. But new experiments have shown that, in some special cases, outside conditions might have an effect. For example, placing certain isotopes in a strong magnetic field or inside special materials might slightly alter their decay rates. These changes are small, but they suggest that half-lives are not as unchangeable as we once believed. Temperature, pressure, and even chemical surroundings can play a role, though usually only in rare or extreme settings. There is also the case of isomers, atoms with the same number of protons and neutrons but with different energy states. Some nuclear isomers are stuck in a high-energy state and can last a surprisingly long time before dropping down to a lower one and releasing energy. Their half-lives might stretch from seconds to decades or more. The reason they wait is not because they are stable in the usual sense, but because the path to decay is blocked. The nucleus wants to change, but it can't do it easily. It's like water behind a dam, ready to flow but held in place by the shape of the structure. And sometimes, decay doesn't even come from the atom itself. A passing particle or a small energy input from the environment can trigger a change in a process known as induced decay. When we start to look at all these factors, we see that the idea of a lifespan becomes harder to define. An atom's life isn't measured like a human's, with a beginning and an end. It's more like a chance, held open over time. The longer an atom goes without decaying, the more unusual it becomes. But it's never impossible. That's why scientists still find radioactive atoms left over from the early days of the universe. They are rare, but not gone. Their decay is just slow enough that they have lasted for billions of years. This also opens up new questions about how we measure time in atomic processes. A half-life assumes a steady decay rate spread evenly over time. But decay happens in jumps, in sudden moments that change the atom completely. Between those jumps, nothing happens at all. Time passes, but the atom stays exactly the same. This makes atomic decay very different from everyday aging. It's not a slow wearing down. It's more like a stillness, waiting for a single event to occur. Some physicists have even explored whether time itself might behave differently at very small scales. In the quantum world, events are not continuous. They come in discrete steps. Could this mean that the passage of time inside an atom is also step-like, not smooth? It may not be enough to ask how long an atom lasts. We might also need to ask how time flows inside it. The half-life has been a helpful tool for predicting decay and managing radioactive materials. It allows us to estimate how long a nuclear medicine will remain active or how dangerous a piece of waste might be, but decay is a mix of chance, structure, and environment. In this light, the half-life becomes a signpost, not a boundary. Entropy's role: increasing disorder at the subatomic level. Ice melts into water. Buildings crumble. Heat spreads from a hot stove to a cool room. All of these are signs of something deeper at work, a rule of nature that governs how energy and matter behave over time. This rule is known as the second law of thermodynamics, and it says that in any closed system, the total amount of disorder, called entropy, will either stay the same or increase. It never decreases on its own. Entropy is often described as a measure of randomness or chaos, but it can also be seen as the number of possible arrangements a system can take. A neatly stacked deck of cards has low entropy because there's only one way to make it that perfect. A shuffled deck has high entropy because there are many ways it could look messy. In nature, most systems tend to move from the neat stack toward the shuffle. The universe prefers disorder, not out of laziness, but because disorder is more likely. At the subatomic level, this same principle holds true. When we look at atoms, especially unstable ones, we find that decay and transformation follow this rule of rising entropy. An atom that is packed with energy, or arranged in a rare and precise way, tends to shift over time toward a more common, lower energy state. The result is a process where order is slowly replaced with a wider range of outcomes. And even though the changes happen in tiny amounts, the direction is always the same, toward more possibilities, more randomness, more entropy. Consider a radioactive atom like uranium. Over time, it might release an alpha particle. That act of decay doesn't just release energy, it also spreads that energy into the surroundings, and it increases the number of particles involved. Where once there was a single atom, now there are smaller pieces, and each of them can move in different ways. The system has more arrangements, more freedom, and therefore more entropy. Even though energy might be thought of as the most important part of atomic reactions, entropy plays an equal role. A transformation may release very little energy, but still happen because it leads to more disorder. In fact, some changes that don't seem energetically favorable can still happen if they create a big enough rise in entropy. It's as if the universe is willing to spend a little energy in order to gain more possibilities. This explains why certain reactions, like the spontaneous mixing of gases or the decay of specific isotopes, occur naturally without being forced. In the microscopic world, the increase of entropy can be hard to notice at first. Atoms do not get messy in the same way that houses do, but the change is real. After a particle decays, the system it was part of becomes more complex. There are now more ways for the particles to move and spread out. The total energy is still there, but the order it once had is gone. In our daily lives, time seems to move in one direction, forward. We watch glasses fall and break, but never reassemble themselves. Systems naturally move toward disorder, and because this increase cannot be undone without extra work, we experience time as moving from low entropy to high entropy. This is true in large systems like planets and stars, and in small systems like atomic nuclei. Entropy explains why some atoms are stable and others are not. A stable atom already sits in a low-energy, high-entropy state. There is little to gain by changing. But an unstable atom, one with too much energy or the wrong number of neutrons, is in a kind of tension. Its current form is unusual, unlikely, and more ordered than it should be. By decaying, the atom finds a new form that's more probable. Entropy helps us understand why atomic decay is usually a one-way street. Once an atom breaks apart or transforms, it does not spontaneously go back to its original form. To reverse the decay, we would need to force the particles back into the same structure, with the same exact positions and energies. That level of order is so specific, so unlikely, that it almost never happens. The atom can fall apart easily, but building it back up requires careful outside help. Without entropy, atomic changes might seem random or wasteful. But with it, we see that each decay adds to a larger story. The small acts of atomic change are part of the vast process that shapes everything from stars to cells. Atomic transformation in extreme environments. In the core of our Sun, temperatures reach over 15 million degrees Celsius. Pressures are millions of times higher than those at the surface of Earth. In this fiery core, atoms are squeezed together so tightly and heated so intensely that they begin to fuse. Hydrogen nuclei slam into one another, combining to form helium. But fusion doesn't happen just because the atoms are close. It takes extreme heat to give them enough speed to overcome their natural repulsion. Protons are positively charged, and like charges, repel each other. In normal conditions, that repulsion is enough to keep atoms apart. But in the heart of a star, particles move so fast that they crash through this barrier. When they finally get close enough, the strong nuclear force, normally short-range and quiet, snaps them together. A new nucleus is born, and in the process, a small amount of mass is turned into a large amount of energy. In such environments, some decay processes that would take thousands or millions of years can happen much more quickly. The added heat and pressure shift the energy balance of the nucleus. For some isotopes, this means they can release particles more easily. Others become more stable in the heat as new forces come into play. Supernovae are another stage for extreme atomic change. In the last moments of a large star's life, the balance between gravity and nuclear fusion fails. The core collapses, pressure spikes, and temperatures shoot up to billions of degrees. Under these conditions, heavy elements like gold, uranium, and plutonium are forged in a matter of seconds. These atoms don't form slowly over time. They are built in an instant under crushing forces that smash lighter elements together. Some atoms decay almost as quickly as they're made, releasing waves of radiation and flooding space with newly formed particles. Others survive, drifting through space until they find new homes in dust clouds, planets, or living things. On Earth, we create extreme environments in places like nuclear reactors and particle accelerators. Inside a reactor, atoms like uranium-235 are bombarded with neutrons. These extra particles destabilize the nucleus, making it more likely to split. When the nucleus breaks apart, it releases energy, more neutrons, and smaller atoms. These new particles can then trigger more fission, creating a chain reaction. This is how nuclear power is generated. The temperature inside a reactor core can climb to thousands of degrees. Neutron levels are kept high to make sure atoms keep breaking apart. This changes the rules. Some isotopes that would be stable in the ground become unstable under bombardment. Others that decay slowly begin to fall apart much faster. The environment changes the timeline of decay and the energy released. In particle accelerators, scientists take things even further. They strip atoms of their electrons, turn them into ions, and then hurl them at each other at near light speeds. When these particles collide, the forces involved are strong enough to break nuclei apart, or even form new particles. Some of these collisions mimic conditions just after the Big Bang. Others let researchers create atoms that don't exist naturally, ones that are too unstable to last more than a fraction of a second. But in that brief moment, they give scientists a glimpse into the extreme behaviors of matter. Deep inside planets like Jupiter, where gravity creates intense pressure, atoms are squeezed to an unparalleled degree. Hydrogen becomes metallic, conducting electricity like a metal. Atoms are pushed closer together than they would ever be otherwise. Their electrons behave differently. Bonds shift. Some atoms begin to decay in ways they wouldn't in open air. In plasmas, the fourth state of matter, atoms are so hot that their electrons are stripped away. The result is a mix of free nuclei and electrons, all moving chaotically. In this state, normal rules start to bend. Electrons can reattach in strange patterns. Atoms can decay in unique ways or form bonds with unexpected partners. Some of the most powerful atomic transformations in the universe take place in the most extreme locations. In neutron stars, matter is packed so tightly that atoms are crushed out of existence, leaving behind a sea of neutrons. In black holes, matter is pulled inward with such force that the rules of physics break down. These are not places where atoms remain stable. They are where atoms are stretched, torn, or reborn into new forms. Nuclear instability, when the core crumbles. For some elements, the delicate balance between the forces within the nucleus is maintained for billions of years, but for others, it can become unstable relatively quickly. What makes the nucleus unstable? As atoms get larger, they require more neutrons to maintain stability. This is because the strong nuclear force can only act over very short distances, so the farther apart the protons are, the weaker the force becomes. Larger atoms, with more protons in their nucleus, need more neutrons to help keep the nucleus intact. If an atom doesn't have enough neutrons, the strong force can't balance the electromagnetic force, pushing the protons apart, making the nucleus unstable. One of the key indicators of instability is the ratio of protons to neutrons in a nucleus. In lighter elements, the balance is relatively straightforward, around 1 neutron for every proton. But as atoms get heavier, the number of neutrons needed for stability increases. In very heavy elements, such as uranium or thorium, the number of neutrons can be much greater than the number of protons. If an atom has too many protons or too few neutrons, the nucleus will become unstable and begin to decay. Another factor that contributes to nuclear instability is the energy state of the nucleus. Every nucleus has a certain amount of energy stored in it, and the configuration of protons and neutrons determines how much energy is needed to keep the nucleus stable. If an atom is in a high-energy state, it might seek a lower energy state by undergoing radioactive decay. For some elements, the instability arises from an excess of neutrons. The strong nuclear force within the nucleus can only hold things together for so long, and eventually the nucleus reaches a breaking point. The extra neutrons create an imbalance that causes the nucleus to emit particles, such as alpha or beta particles, to release some of the excess energy. In this way, the atom attempts to reach a more stable state by shedding parts of its nucleus. For other elements, such as certain isotopes of iodine or carbon, the imbalance is caused by having too many protons. The electromagnetic repulsion between these positively charged particles becomes too much for the strong nuclear force to contain, causing the nucleus to break apart. This type of instability typically leads to beta decay. While the strong nuclear force tries to hold the protons and neutrons together, other forces like the electromagnetic repulsion between protons work against this force. When these forces become unbalanced, the nucleus is no longer stable. The nucleus may then break apart through various forms of radioactive decay in an attempt to reach a more stable state. Each type of decay represents a different way that the nucleus attempts to reach stability. In some cases, the decay leads to the emission of a single particle. In others, it can result in the transformation of one element into another. These changes often involve a release of energy in the form of radiation. This is why radioactive materials can be so dangerous. When atoms undergo these transformations, they release energy that can be harmful to living organisms. Quantum tunneling, escaping the nuclear barrier. Unlike the everyday world we're used to, the behavior of particles inside an atom doesn't follow the simple rules of classical physics. Instead, particles can behave in ways that seem completely counterintuitive to our understanding of how objects should behave. One of the most remarkable examples of this strange behavior is a phenomenon known as quantum tunneling. Quantum tunneling is a concept in quantum mechanics that describes how particles can sometimes pass through barriers that they should, according to classical physics, never be able to cross. If we think about a particle, like a proton, approaching a barrier, classical physics tells us that the proton will either crash into the barrier or bounce back, depending on its energy. It shouldn't be able to just pass through the barrier unless it has enough energy to overcome it. But in the quantum world, things don't work that simply. Instead of being blocked, particles can tunnel through the barrier, even if they don't have enough energy to overcome it in the traditional sense. According to quantum theory, particles don't have a precise position or energy. Instead, they exist as a cloud of probabilities, meaning they have a range of possible positions and energies. When a particle approaches a barrier, quantum mechanics tells us that the particle is not just confined to one place. Instead, it can spread out over the barrier and have a non-zero chance of being on the other side. The key to this behavior lies in the wave-like nature of particles. In quantum mechanics, particles are described by wave functions, which give the probability of finding the particle in a given location. These waves can spread out across space, and even when encountering an energy barrier, part of the wave can extend into and even through the barrier. The wave function continues on the other side, albeit with a lower probability of finding the particle there. The result is that the particle has a small but non-zero chance of being on the other side of the barrier, even if it doesn't have enough energy to overcome it in a classical sense. This is the essence of quantum tunneling. One of the best-known examples of tunneling occurs during alpha decay. In order for the alpha particle to escape the nucleus, it has to overcome a potential barrier created by the strong nuclear force and the electrostatic repulsion between the positive charge of the alpha particle and the positively charged nucleus. Classically, this would be impossible because the alpha particle simply doesn't have enough energy to overcome this barrier. The strong force is powerful, and the electrostatic repulsion is significant. Yet, in the quantum world, things are different. When the alpha particle approaches the barrier, it doesn't need to have enough energy. Instead, it can borrow some of the energy from the quantum system, allowing it to tunnel through the potential barrier. The particle doesn't simply climb over the barrier, it appears on the other side. This process allows the atom to undergo alpha decay, despite the fact that the particle does not have the energy to surmount the barrier traditionally. The probability of quantum tunneling occurring depends on several factors. One of the most important is the thickness and height of the barrier. A thicker or higher barrier makes tunneling less likely, as the particle's wave function has a smaller chance of reaching the other side. However, if the barrier is thin enough and the particle is close enough to the barrier, tunneling becomes more likely. This explains why certain isotopes decay at specific rates. Some nuclei have barriers that are thin enough for tunneling to occur relatively easily, while others have thicker barriers that make tunneling much rarer. Quantum tunneling also plays a role in other forms of radioactive decay and nuclear reactions. In some types of beta decay, where a neutron transforms into a proton, tunneling can also be involved. The probability of tunneling helps determine the rate at which these decay processes occur. The same basic principle applies. Particles don't need to have enough energy to overcome a barrier. Instead, they have a chance to tunnel through it. Quantum tunneling is also responsible for other phenomena in the atomic world. In nuclear fusion, tunneling allows protons to overcome the repulsive electromagnetic force between them. Hydrogen nuclei are heated to extreme temperatures and they move incredibly fast, but they still don't have enough energy to overcome the electrostatic repulsion between them. Thanks to quantum tunneling, however, the protons can still tunnel through the barrier and fuse together, forming helium and releasing a tremendous amount of energy in the process. Without tunneling, nuclear fusion would not be possible at the temperatures found in stars. Quantum tunneling also influences the behavior of semiconductors and superconductors. This has profound implications for the design of modern electronics and technologies, such as transistors and quantum computers. Atomic fate in high-energy collisions. When two particles collide at speeds close to the speed of light, the energy involved can be enormous. In these extreme conditions, the forces that typically bind the protons and neutrons together are pushed to their breaking point. This can result in the disintegration of the nucleus, a process called nuclear fragmentation. In a particle accelerator, particles are accelerated to speeds so high that their energy is sufficient to overcome the forces holding the nucleus together. In these collisions, the nuclei of atoms can break apart in a variety of ways. The exact outcome of the collision depends on the types of particles involved, the energy of the collision, and the conditions in the surrounding environment. In many cases, the result is the creation of new particles and even entirely new atoms. At extremely high energies, the strong nuclear force can become overwhelmed by the intense kinetic energy of the colliding particles. When this happens, the nucleus of the atom may become unstable and split apart. High-energy collisions can lead to nuclear fission. This is the principle behind nuclear reactors. However, when the energy involved in the collision is high enough, it can cause the nucleus to fragment into even more pieces. Instead of just breaking into two fragments, the nucleus may shatter into several smaller nuclei, along with a variety of other particles, in a process called multifragmentation. The different kinds of particles include mesons, which mediate the strong nuclear force, and other types of subatomic particles that are not typically found in stable matter. The creation of these particles can provide valuable insight into the fundamental forces at work within the atom and the interactions between different types of matter. In some cases, these collisions can generate entirely new elements. Isotopes of existing elements can also be created. This process is a key part of nuclear physics research, and it helps scientists understand how elements are formed in the universe. Researchers can create heavy elements that do not exist naturally on Earth, such as elements found in the so-called island of stability. These heavy elements are often highly unstable. but their existence can help scientists explore the boundaries of the periodic table and gain insights into the structure of matter itself. In extreme cases, the energy from the collision can be so high that it destroys the atoms involved, breaking them down into fundamental particles like quarks and gluons. These particles, which make up protons and neutrons, exist at the most basic level of matter. When atoms are disintegrated in high-energy collisions, scientists can study these elementary particles to gain a deeper understanding of the forces that govern the behavior of matter. In addition to the destruction of atoms, high-energy collisions can also lead to the creation of exotic states of matter. Scientists have been able to recreate the conditions just moments after the Big Bang. Back then, matter existed in a hot, dense plasma of quarks and gluons. This state of matter, known as quark-gluon plasma, is thought to have existed in the early universe before the protons and neutrons that form atomic nuclei were created. The most famous particle accelerator, the Large Hadron Collider, or LHC, at CERN, allows scientists to study the behavior of particles at energies never before achieved. These experiments are helping researchers explore the basic building blocks of matter and search for new phenomena that could help explain some of the most profound mysteries of the universe, such as the nature of dark matter and dark energy. Energy redistribution, the aftermath of decay. When an atom undergoes decay, the process is not just about the breakdown of matter, but also the release of energy. This energy is redistributed into the surrounding environment, often in the form of radiation, heat, or kinetic energy. What happens to this energy, and how it interacts with its surroundings, is a crucial part of the decay process. As an atom decays, it can emit different types of energy depending on the type of decay occurring. For example, in alpha decay, the nucleus releases an alpha particle, while in beta decay, an electron and an antineutrino are emitted. In both cases, the energy from the transformation is carried away by these particles, and the energy carried by the emitted radiation has to go somewhere. This radiation is usually released in the form of kinetic energy, carried away by the particles. In some cases, the energy may be converted into electromagnetic radiation, such as gamma rays. Gamma rays are high-frequency electromagnetic waves that carry a significant amount of energy and can travel vast distances, carrying their energy with them. This energy can be absorbed by other materials, which can cause those materials to heat up, or in some cases, to undergo their own transformations. In some instances, gamma radiation can cause other atoms to become excited, knocking electrons out of their orbits or inducing further ionization in the material. This effect can be seen in the way materials like metals and gases react when they are exposed to high levels of gamma radiation, often becoming ionized or heated to high temperatures. In nature, the process of radioactive decay is responsible for a wide range of phenomena. For example, in the Earth's crust, naturally occurring radioactive isotopes such as uranium and thorium release energy as they decay. This energy contributes to the overall heat of the planet, playing a crucial role in maintaining the Earth's internal temperature. The heat generated by the decay of radioactive materials in the Earth's core is one of the key drivers behind geological processes such as plate tectonics and volcanic activity. These processes, in turn, influence the surface of the planet, shaping continents, mountains, and ocean basins. One of the most important applications of the energy released during decay is in the field of nuclear power. This energy is absorbed by the nuclear reactor's coolant, which is then used to produce steam and drive turbines to generate electricity. The process of energy redistribution in a nuclear reactor is carefully controlled, with the energy from the decay being harnessed and used for power generation. In certain medical treatments, radioactive isotopes are used to target and treat cancer cells. In radiotherapy, high-energy radiation is directed at tumors, and the energy from the decay of radioactive isotopes damages the DNA of cancer cells, preventing them from growing and dividing. The energy released during this decay is focused on a specific area of the body, minimizing damage to healthy tissue while effectively treating the cancer. In diagnostic imaging, radioactive isotopes are used in techniques like positron emission tomography, or PT, scans, where the energy released from the decay of the isotopes helps to create detailed images of the inside of the body. In environments where the energy is released without such precautions, it can have significant and dangerous effects. High doses of radiation can damage living tissues, leading to burns, genetic mutations, or even death. The energy from radioactive decay can also lead to the formation of reactive chemical species, such as free radicals, which can cause damage to cells and DNA. This is why radioactive materials are handled with such care, both in laboratory settings and in industries like nuclear power, where there are stringent measures in place to control and limit exposure to radiation. When radioactive decay releases energy, it can cause the surrounding material to heat up. This heating effect can cause the material to expand or undergo other physical changes. In certain types of radioactive waste disposal, the heat generated must be carefully managed to prevent the waste containers from overheating. Beyond practical applications, the way energy from decay redistributes also raises intriguing questions about the fate of energy in the universe. Energy tends to move from areas of higher concentration to areas of lower concentration. In the case of radioactive decay, energy spreads out from the nucleus of the decaying atom and dissipates into the surroundings, increasing the overall entropy of the system. When an atom undergoes decay, the energy released is transformed from the potential energy stored within the atom's nucleus into kinetic energy, or electromagnetic radiation. In this way, decay is also a process of energy transformation. Phase transitions within the atom. Just as matter can transition from one state to another under different conditions of temperature and pressure, like water freezing into ice or boiling into steam, so too can atomic systems transition in ways that alter their behavior and properties. The structure of the atom itself can shift, leading to significant changes in how atoms behave within a material. These changes might not always be as dramatic as ice melting into water, but they can still represent a kind of phase transition that fundamentally alters the properties of the material. One of the most well-known atomic phase transitions occurs when the electrons within an atom are excited from their lowest energy levels to higher ones. This happens when an atom absorbs energy, often in the form of light. The electrons, which normally occupy specific energy levels, can jump to higher levels if they absorb enough energy. This process is similar in some ways to how a solid turns into a liquid when enough heat is applied. When electrons are excited, the atom moves from a more stable configuration to a higher energy state, altering its behavior. If the atom releases the energy, the electron returns to its original energy level. These transitions are governed by the principles of quantum mechanics, where the energies of electrons are quantized, meaning they can only occupy specific energy levels. The shift between these levels is often called an electronic transition. While this is one form of transition within atoms, the most striking phase transitions occur when the internal structure of the atom itself is fundamentally altered. One example of such a transition is nuclear fission. This transition of splitting, while not a phase transition in the traditional sense, mirrors the way a material might break apart when it reaches a critical temperature. The critical energy needed to induce fission serves as the key that causes this internal atomic transformation. Both nuclear fission and fusion are examples of atomic phase transitions that result in the formation of new elements or the release of large amounts of energy. However, not all atomic transitions result in such a thing. There are also phase transitions that occur at the level of the electron cloud surrounding the nucleus. In certain materials, the arrangement of electrons can change depending on the external conditions, like temperature or pressure. This can lead to what's known as a metal-to-insulator transition or a superconducting transition, where the behavior of the material changes drastically and the material moves from conducting electricity to not conducting at all, or vice versa. In quantum systems, phase transitions may not always be tied to temperature or pressure alone. They may also be influenced by the quantum mechanical interactions between particles. This has led to the discovery of phenomena like quantum critical points, where a material can exist at the edge of different phases, with its behavior constantly shifting based on the interactions within the atomic structure. Atomic death in the gravitational maelstrom. The powerful gravitational fields near these celestial objects have a profound effect not only on massive stars and planets, but also on the atoms that make up matter itself. The influence of gravity, particularly near black holes, introduces a whole new dimension to our understanding of atomic behavior. Black holes are regions in space where gravity is so strong that not even light can escape. They represent the ultimate distortion of space-time, causing anything that ventures too close to become trapped in their gravitational pull. These objects are surrounded by what is called the event horizon, a boundary beyond which no information, not even light, can escape. This extreme environment exerts immense forces on the objects nearby, causing time to stretch and space to bend in ways that are not immediately intuitive. One of the most striking consequences of being near a black hole is the warping of time itself. As an object approaches the event horizon, time appears to slow down relative to an observer farther away from the black hole. This phenomenon, known as time dilation, occurs because gravity itself influences the passage of time. For an atom close to the event horizon, this means that its decay process could appear to slow down from the perspective of an external observer. The atom might seem to linger in its decaying state, taking longer to undergo its transformation than it would in a less intense gravitational field. On the flip side, from the perspective of an observer near the black hole, the decay process might seem to happen much more rapidly. The distortion of time and space near the event horizon could cause the decay process to appear accelerated when viewed from within the strong gravitational field. These conflicting perspectives arise because of the way gravity alters the flow of time. What seems like a normal, predictable decay in one frame of reference may appear as a dramatically different process in another. But gravity near black holes doesn't just affect the passage of time. The intense forces can also influence the stability of the atomic nucleus itself. Under normal circumstances, the nucleus remains stable as long as the balance between the nuclear forces is maintained. However, when an atom is placed in an environment with extreme gravitational forces, the balance of these forces can be disrupted. The tidal forces near a black hole, essentially the stretching and compressing caused by the uneven pull of gravity, can distort the nucleus itself. This could potentially lead to a faster breakdown of the atomic structure. The gravitational forces could tear apart atomic nuclei, breaking the bonds between protons and neutrons, and forcing the atom to undergo a type of decay that is driven not by quantum processes, but by the external forces of gravity. This could lead to an increase in the rate of decay, with the atom fragmenting in a manner that is entirely influenced by the gravitational environment rather than its intrinsic properties. Plasma states, when atoms are torn apart. Atoms begin to break down when exposed to extremely high temperatures and energies. This breakdown leads to the creation of plasma, where the usual boundaries between the different components of an atom begin to blur, and the material enters a state that behaves very differently from the matter we normally interact with. In normal conditions, atoms remain electrically neutral, with the positive charge of the nucleus balanced by the negative charge of the electrons. But when a material is exposed to extremely high temperatures, the kinetic energy of the particles becomes so high that the electrons can no longer remain bound to their atomic nuclei. This ionization leads to the creation of plasma. What was once a neutral atom is now split into positively charged ions in the form of the nucleus, and negatively charged electrons, floating independently in a chaotic, highly energetic state. In the plasma state, the ions and free electrons move freely and interact in ways that differ drastically from their behavior in other states of matter. Unlike in solids, where atoms are tightly packed together in orderly structures, or in liquids, where atoms are more loosely connected but still retain some structure, plasma is characterized by a lack of any stable atomic organization. The ions and electrons in a plasma are constantly moving and interacting, influenced by both the extreme temperature and the electromagnetic forces that are present. Because of this dynamic, the properties of plasma are dramatically different from those of gases, even though plasma technically falls under the broader category of gases. Plasma is highly conductive, affected by electric and magnetic fields, and can emit light, which is why we see phenomena like the glowing auroras or the intense brightness of a star. Stars, including our own Sun, exist in a constant state of plasma, with their cores reaching temperatures of millions of degrees. Thermonuclear fusion is only possible in the plasma state, where atoms are no longer individual, stable entities. The intense heat and pressure in the core of a star strips electrons away from the atoms, and what results is a superheated soup of nuclei and free electrons moving at incredible speeds. As the plasma reaches the outer layers of the star, it cools and condenses, eventually forming the gas-like outer layers we can observe. However, the inner core remains a dense, hot plasma, continuously undergoing fusion. Plasma also forms during explosive events such as supernovae. When massive stars reach the end of their life cycle, the core of the star contracts under its own gravity and temperatures soar to levels high enough that matter breaks down into plasma. In a supernova, the sheer force of the explosion causes atoms to undergo rapid ionization, creating a shockwave of plasma that tears apart the surrounding star. The explosion of a supernova can release a staggering amount of energy, and the plasma it creates is a key component of this event. In the aftermath of a supernova, the remnants of the star, often in the form of a nebula, are made up of a highly energetic ionized gas. This plasma, now cooling and expanding, will eventually condense to form new stars and planets, but it is initially a chaotic, superheated environment. Plasma is created in a number of laboratory experiments, often involving particle accelerators or high-energy lasers. In these environments, scientists study plasmas to better understand the fundamental interactions of matter under extreme conditions. Plasma is also commonly found in technologies like fluorescent lights, plasma TVs, and even in the controlled fusion experiments that aim to replicate the energy-producing processes of stars. Another fascinating example of plasma on Earth is the phenomenon of lightning. A lightning bolt occurs when electrical charges build up in the atmosphere, creating a powerful discharge of energy. As this discharge travels through the air, it ionizes the gas molecules, turning the air into plasma. This plasma path allows the lightning to travel at incredibly high speeds, heating the surrounding air to temperatures hotter than the surface of the sun. The bright flash of light associated with lightning is the result of the plasma's high energy, and the sound of thunder comes from the shockwave created by the rapid expansion of the heated air. Because plasma consists of charged particles, it is highly responsive to external electromagnetic forces. This is why we see plasma in many phenomena that involve these fields, such as the aurora borealis or the northern lights. The Earth's magnetic field directs charged particles from the sun, funneled into the atmosphere, where they interact with gases like oxygen and nitrogen to produce the colorful light displays we observe in the polar regions. These lights are the result of electrons recombining with ions in the atmosphere, releasing energy in the form of light. What makes plasma particularly interesting from a scientific perspective is how the behavior of atoms changes when they reach this state. These interactions can lead to a variety of phenomena, such as plasma waves, magnetic confinement, and the formation of structures like plasma filaments and jets. In some environments, plasmas can even become so dense that they resemble a kind of liquid phase, exhibiting collective behavior that is not seen in other states of matter. As we study plasma more deeply, scientists continue to find new ways to manipulate and understand it. In the quest for nuclear fusion energy, for example, scientists are attempting to create and control plasma in a way that could provide a nearly limitless source of clean energy. In these experiments, called magnetic confinement fusion, plasmas are created and confined using powerful magnetic fields. The goal is to create a plasma state similar to the one found in the Sun's core, where the temperature and pressure are high enough to sustain fusion reactions. If successful, this technology could provide a clean, sustainable energy source for humanity. From particle to wave, the dual nature of atomic debris. To understand how decay products can be both particles and waves, it helps to look at the most famous example of wave-particle duality, light. In the early 20th century, scientists discovered that light behaves in a way that can't be fully explained by classical physics. On one hand, light can be described as electromagnetic waves, as it travels through space, bending and interfering like any wave. However, light also shows particle-like behavior. When light is shone on a metal surface, it can eject electrons from the surface, a phenomenon known as the photoelectric effect. This behavior suggests that light is also made up of discrete packets of energy called photons. This idea of wave-particle duality was extended to all particles, including those produced in atomic decay. Take the example of an alpha particle. In classical terms, an alpha particle is a solid, discrete object, like a tiny ball. However, in the quantum world, this particle can also be described as a wave, with its position and momentum not fully determined until it interacts with other objects. Its behavior can be influenced by the surrounding environment in ways that are reminiscent of a wave traveling through space. For instance, when an alpha particle moves through matter, it may undergo a phenomenon called diffraction, which is typically associated with waves. The particle will bend or spread out in specific patterns depending on the material it's passing through. Even more striking is the behavior of gamma rays, which are simply very high-energy photons. While gamma rays travel through space as waves, they can also be thought of as particles when they interact with matter. They exhibit the photoelectric effect and excel at knocking electrons out of their orbits. Every particle is described by a wave function, a mathematical function that encodes information about the probability of finding the particle in a particular place at a particular time. The wave function allows us to calculate the likelihood that a particle will exhibit wave-like or particle-like behavior under specific conditions. When we observe a particle, its wave function collapses, and we see it as a definite particle. However, in the absence of such an observation, the particle's wave function describes a spread-out distribution of possibilities, much like a wave. The exact moment of decay and the type of radiation emitted are fundamentally probabilistic, governed by quantum mechanics. The probability that a particular decay will occur and the type of radiation that will be emitted depends on the wave function associated with the unstable atom. The decay product, once emitted, continues to exhibit dual behavior, sometimes acting like a particle and other times behaving like a wave, depending on the situation. In detectors, radiation can be measured both as discrete particles and as continuous waves. The detectors themselves, whether they are scintillation counters, ionization chambers, or semiconductor detectors, are designed to capture and measure these waves or particles, depending on the type of radiation and the desired measurements. Why do particles behave this way? Why can something as tiny as an electron or photon switch between particle and wave behavior depending on the situation? These questions remain at the forefront of theoretical physics and continue to challenge our understanding of the fundamental nature of reality. Virtual particles and the vacuum, an atomic perspective. A vacuum at first glance might seem empty and devoid of anything. But in the quantum realm, this empty space is far from still. It is teeming with brief, fleeting particles that pop in and out of existence. Although virtual particles can't be directly observed, their presence influences the behavior of decaying atoms in profound ways. The term virtual particle is a bit misleading. Unlike the particles we encounter in the everyday world, virtual particles are not permanent entities that we can measure or detect directly. Instead, they are temporary disturbances in a quantum field that exist for an incredibly brief moment, only to disappear soon after. They are called virtual because they don't obey the traditional laws of energy and momentum that real observable particles follow. While these virtual particles are short-lived and cannot be detected in the same way as real particles, they still exert a real effect on the world around them. The idea of virtual particles arises from the principles of quantum field theory, which describes how fields exist throughout space, even in what appears to be a vacuum. These fields are not empty, but filled with energy and potential, even in the absence of real particles. Think of these fields as a vast ocean, with virtual particles constantly creating tiny waves that ripple through the water, then disappearing before they can be fully observed. In quantum field theory, the vacuum is constantly fluctuating. For instance, in a process called vacuum polarization, virtual particles can create an electric field that influences the behavior of nearby real particles. The fluctuating virtual particles effectively modify the properties of the vacuum, changing how real particles interact with it. In processes like beta decay, virtual particles can mediate the interactions between the decaying particle and the forces involved. More specifically, the virtual particles involved are often tied to the fundamental forces at play, like the weak nuclear force, which governs processes like beta decay. The weak force itself is not something that we can observe directly. It is transmitted by virtual particles, typically W and Z bosons. These particles are responsible for enabling the decay process in the first place, and their brief existence helps facilitate the exchange of energy that ultimately leads to the transformation of one particle into another. In certain high-energy environments, virtual particles can create conditions that influence the rate of decay or even cause a decay to occur at a different energy level. One of the most striking examples of the role of virtual particles comes from the phenomenon known as the Casimir effect. In this effect, two metal plates placed very close together in a vacuum will experience an attractive force due to the fluctuations of virtual particles in the vacuum. The plates act to restrict the types of virtual particles that can appear between them, leading to a pressure difference between the inside and the outside of the plates. This effect, while incredibly subtle and small, demonstrates how the presence of virtual particles can influence the behavior of real objects, even in the seemingly empty vacuum. Virtual particles are what allow the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, to operate in the quantum realm. Without these brief disturbances in the quantum field, the interactions that govern the behavior of matter and energy would not function in the way that we observe in the physical world. In a sense, virtual particles are the hidden players in the quantum world. They are there, shaping the outcome of atomic processes, influencing the behavior of particles and fields, but remaining just out of reach of direct observation. Their fleeting nature, combined with the fact that they do not conform to the same rules as real particles, makes them a fascinating and elusive aspect of quantum physics. Entanglement and decay, a quantum web. Quantum entanglement is a phenomenon that Albert Einstein once famously described as spooky action at a distance. This spooky action refers to how two particles can become entangled in such a way that their properties, such as spin, momentum, or polarization, are interdependent, even if they are far apart. The behavior of one particle immediately affects the other, regardless of the physical distance between them. This is one of the most puzzling aspects of quantum mechanics, and it has become a cornerstone of modern physics. When an atom decays, the particles it releases don't simply fly off in a random direction, they can become entangled with each other. This entanglement happens when two or more particles are produced in such a way that their quantum states are linked. The properties of one particle can immediately affect the properties of the other, even if the particles are separated by vast distances. Once entangled, the connection between these particles persists, no matter how far apart they are. This means that when one particle changes its state, the other will change as well, even if they are on opposite sides of the universe. Entanglement is often illustrated by using the example of a pair of particles created in a specific quantum state. Imagine a pair of particles that are emitted during the decay of a radioactive atom. If these particles are entangled, their individual properties, such as the direction they move or the specific energy they carry, are not determined until they are observed. Until observation, these properties exist in a state of probability, and only when we measure one of the particles does the state of the other become defined. This is what Einstein found so puzzling. How can the state of one particle instantaneously affect another, no matter the distance? Consider two particles emitted during the decay of a parent atom. One might be an electron and the other a neutrino. These particles are created simultaneously and their quantum states are interconnected. If the electron spins in a particular direction, the neutrino's spin will automatically align in the opposite direction, even if the two particles are light years apart. This can happen regardless of the environment or the changes that occur in the atomic system from which they came. Their connection is unbreakable in the sense that the measurement of one particle directly impacts the state of the other. The relationship between particles created during atomic decay isn't limited to simple pairings. In fact, a number of particles might be entangled in various combinations. In a phenomenon known as quantum superposition, particles can exist in multiple states at once until they are measured. The decay of an atom may lead to a cascade of entangled particles, creating a complex network where every particle's behavior is tied to the others in a deeply interconnected way. This quantum web makes the process of atomic decay far more intricate than just the emission of particles into empty space. Every decay event could, in theory, affect other systems, spread across the quantum field. For example, a nuclear decay might trigger the creation of several entangled photons, each carrying information about the nature of the decay. As these photons travel outward from the source, they remain linked in their quantum states. If one photon interacts with another particle, perhaps a distant atom or a detector, it will immediately affect the state of the entangled photon, even if the two photons are separated by vast distances. This phenomenon, known as non-locality, is a core feature of quantum mechanics. Understanding this web of entanglement has opened up new pathways for developing technologies like quantum computing and secure communication systems. Entangled particles seem to defy the classical idea that information should travel at a finite speed. Instead, information about the state of one particle seems to be immediately transferred to the other, regardless of the distance separating them. This opens up the possibility that information may not be as bound by time and space as we once thought. Rethinking death in a quantum world. A living organism dies when its systems shut down. A machine dies when it stops working and can't be restarted. Even in classical physics, we tend to speak of systems reaching an end, an object losing motion due to friction, a star running out of fuel, or an atom decaying into smaller parts. But when we enter the world of quantum mechanics, the concept of death becomes harder to define. When we say an atom dies, we often mean it has decayed, that it has lost a particle, changed into a different element, or stopped existing in its original form. But quantum mechanics doesn't see this as a full stop. It treats this change as just one of many possible transitions. In quantum terms, a system doesn't disappear. It evolves. The wave function may collapse or spread, but it doesn't face a final curtain in the traditional sense. The same applies to particles. When a particle is said to decay, it splits into other particles, often ones that are lighter or more stable. This process might seem like a form of death for the original particle, but the pieces it leaves behind continue to exist and interact with the world. The total energy and information carried by the particle don't just vanish. They're conserved and carried on by the decay products. This idea becomes even more complex when considering quantum superposition. A particle might be decayed and not decayed simultaneously, at least until it is observed. It's not until someone measures or interacts with the system that the superposition collapses into one definite outcome. So, if decay only happens upon observation, what does that say about death? Is it even real, or is it just a matter of perception? The famous thought experiment known as Schrödinger's cat plays with this idea. Imagine a cat in a box with a device triggered by atomic decay. If the atom decays, the device kills the cat. If not, the cat lives. According to quantum theory, until someone opens the box and checks, the cat is both alive and dead. It exists in a superposition of both states. The thought experiment forces us to ask, can we truly talk about death in quantum terms if outcomes aren't definite until observed? There's also the matter of quantum entanglement. If one particle decays or changes, the entangled partner responds immediately. But if the original particle dies, does its influence vanish? Not necessarily. The entanglement doesn't disappear just because the particle's form has changed. Some information about the original particle can still be present in the partner. Another twist comes from quantum field theory, where particles are seen not as standalone objects, but as excitations in fields that stretch across space. When a particle decays, the field doesn't vanish. It remains in the background, and new excitations can rise from it. In this view, the particle's death doesn't erase its origin. It's more like a ripple fading in water, while the water itself remains. Even when we try to apply the idea of death to systems that are more complex than single particles, the lines remain blurry. Consider a quantum computer. Its qubits can exist in multiple states at once, and interference between these states is what allows the computer to solve problems classical computers can't. When the system loses coherence, when quantum information leaks into the environment and the qubits stop acting in unison, we might say the computation has failed or died. But even then, the information hasn't vanished. It's just been scattered into surrounding systems in a process called decoherence. Again, what looks like an end is actually a change in form and arrangement. In classical terms, death often means the loss of information. But in quantum mechanics, there's a strong belief that information is never truly lost. Even in extreme scenarios like black holes, where matter seems to vanish beyond the event horizon, physicists debate whether information is destroyed. Some theories suggest that the information is somehow preserved on the black hole's surface or released in subtle ways as the black hole evaporates. If information can never be truly lost, even when particles break down, decay, or fall into black holes, then death loses much of its meaning. It becomes harder to justify calling something dead if its trace, its data, or its impact continues to echo through the quantum world. We can also consider the uncertainty principle, one of quantum mechanics' key features. It tells us we can never know everything about a particle's state at once. If we know its position, we can't know its momentum exactly, and vice versa. This built-in fuzziness means we can't even define a particle's death in sharp final terms. We might think it has decayed, but our ability to measure and describe that process has limits. We are always dealing with probabilities, not certainties. That lack of sharp boundaries makes it hard to declare anything fully gone. In labs where particles are observed decaying, there's always a cloud of uncertainty around when exactly the decay occurs, what path it follows, and what intermediate states it may pass through. There's no sharp line separating existence from non-existence, just a shifting pattern of likelihoods. All of this suggests that in the quantum world, death isn't a clean break. Particles transform, fields ripple, information spreads, and effects linger. The classical idea of death, of a total final stop, may simply not apply. Rather than speaking of death, we might need to speak of transitions, of reconfigurations, of redistributions. In a world where everything is always interacting, shifting, and becoming something else, the line between life and death, presence and absence, becomes more like a blur. The boundaries we take for granted start to dissolve, revealing a universe where nothing ever truly ends. It simply takes on a new form. Annihilation, when an atom meets an anti-atom. When matter meets antimatter, the result is one of the most dramatic transformations known to physics. Annihilation. It's not an explosion in the ordinary sense, but something more fundamental. It's the complete conversion of mass into energy, with no solid fragments or particles left behind. It's a process where the matter that once held structure, atoms, electrons and all simply vanishes into pure radiation. Antimatter atoms are nearly identical in structure, but have opposite electric charges for each particle. Instead of a proton with a positive charge, there is an antiproton with a negative charge. Instead of an electron with a negative charge, there is a positron with a positive charge. Neutrons and antineutrons are a bit more complex since they are neutral, but they still differ in other properties like magnetic moment and the way they behave under certain interactions. When an atom and an antiatom meet, they don't slowly combine or simply mix together. The opposing particles attract each other with a powerful force, especially the particles with opposite charges. A positron, for instance, is drawn strongly toward an electron. When they collide, they cancel each other out. They don't bounce off or stick together. Instead, both disappear in a flash of energy. This process is annihilation. In the case of an electron meeting a positron, the result is typically 2 gamma-ray photons. The total energy of the 2 gamma rays equals the mass of the electron and positron, following Einstein's E equals mc squared. Even though electrons and positrons are incredibly small, the energy released can be intense, because even a tiny amount of mass contains a great deal of energy. This is what makes matter-antimatter annihilation so powerful and so fascinating. If an entire atom meets an entire anti-atom, the process is even more complex. First, the outer particles, the electrons and positrons, annihilate. Then the nuclei begin to interact. The protons and antiprotons collide and also annihilate, often producing more energetic particles. Neutrons and antineutrons can create similar effects. The result is not just gamma rays, but a shower of different particles, more photons, neutrinos, pions, and other short-lived fragments. These fragments quickly decay or fly off into space, carrying away the energy that once existed as structured matter. One of the remarkable aspects of this process is how total it is. In normal collisions between matter particles, even if they break apart or fuse, something physical always remains. There are new particles, or at least fragments of the originals. But with annihilation, nothing of the original particles remains. It's a clean exchange. Mass transforms into energy without leftovers. The structure that made up the atom is gone. What's left is radiation and motion, speeding off into space. This event has been seen many times in labs, especially in particle accelerators where scientists create and study antimatter under controlled conditions. When positrons are created and allowed to interact with ordinary matter, annihilation events can be recorded and measured. When positrons meet electrons inside our bodies during a PET scan, they annihilate, releasing gamma rays which are used to create images of processes inside the body. Despite how energetic and well understood this process is, antimatter is very rare in the universe today. The reason for that is still one of the big mysteries in physics. At the time of the Big Bang, it's believed that matter and antimatter were created in nearly equal amounts. But somehow, matter became slightly more abundant. For every billion pairs of particles and antiparticles, there was one extra particle of matter. When all the rest annihilated, that tiny leftover became everything: the stars, planets, galaxies, and life. Why that imbalance occurred is unknown, but without it, the universe would be filled with nothing but light, no matter, and no atoms at all. Another mystery is how antimatter behaves under gravity. In theory, it should fall just like regular matter. But scientists continue to test this. Recently, experiments have been set up to observe how anti-hydrogen atoms move under the influence of Earth's gravity. If it behaves differently, even slightly, it could challenge many assumptions about the symmetry between matter and antimatter. So far, no difference has been observed, but the data is still being refined. Annihilation follows the rules of conservation, so the energy released depends not just on the mass involved, but also on how the particles are moving when they collide. If they collide at high speed, the resulting energy is even greater. In particle accelerators, atoms and antiatoms can be pushed to nearly the speed of light before they meet. making the annihilation even more powerful and producing a wider variety of outcomes. In cosmic settings, matter-antimatter collisions might still happen in rare conditions. Some theories suggest that there could be entire regions of space dominated by antimatter. If such a region met a matter-dominated region, the boundary between them would light up with constant annihilation events, flashes of gamma rays, too powerful to miss. So far, we haven't seen any sign of these boundaries, suggesting that if antimatter regions exist, they are very far from us. Still, space is vast, and the possibility hasn't been ruled out. In supernovae and around black holes, conditions become extreme enough that particles and antiparticles can be created from pure energy. In those moments, as the gravitational energy becomes intense and temperatures rise into the billions of degrees, photons can turn into particle pairs. But these particles usually find each other again and annihilate quickly before they can drift far. These flashes contribute to the high-energy glow we sometimes detect from cosmic sources. The annihilation of atoms and anti-atoms is one of the clearest examples of the unity between matter and energy. It shows how physical structures, as real and solid as they seem, can be undone completely, turned back into the basic stuff of the universe: energy, light, radiation. It's a reminder that the things we call matter are not permanent. They are temporary arrangements of particles, built and unbuilt by the forces of nature. Simulating atomic demise, computational models, and insights. With modern computing power, scientists can now simulate atomic decay in a virtual space, allowing them to explore what happens when particles break apart, without ever having to physically recreate those conditions. This approach gives researchers the chance to study events that might be too dangerous, too rare, or too fast to observe directly. At the heart of these simulations are mathematical models built from the known rules of physics. These models are carefully designed to follow what we already understand about atomic structures, quantum mechanics, and nuclear interactions. They take into account things like the forces between protons and neutrons, the energy levels of electrons, the way particles behave under pressure or heat, and how radioactive decay progresses. By feeding this information into a computer, researchers can create a sort of digital atom, then run experiments on it using nothing but code. One major advantage of simulations is that they allow us to slow things down. Atomic decay happens incredibly fast, often in fractions of a second that are impossible to see with even the best detectors. In a computer, time can be stretched. Researchers can watch, moment by moment, as a particle wobbles, interacts with its neighbors, and eventually transforms. Every movement, every shift in energy can be recorded and analyzed in great detail. Scientists can simulate exotic forms of matter, unstable isotopes, and rare decay pathways. For heavy nuclei like uranium-238, the breakdown involves multiple decay steps, often releasing alpha particles, beta particles, and gamma rays along the way. In a simulation, each of these events can be tracked, helping scientists understand which path the decay is likely to follow and what particles will be left behind. But building a simulation like this isn't easy. It requires solving complex equations that describe how particles behave. Many of these equations come from quantum mechanics, where uncertainty plays a major role. Instead of predicting a single outcome, the model might have to calculate many possible outcomes, each with a different probability. This means running the same simulation thousands or even millions of times to get a clear picture of what usually happens. High-performance computing is key to this process. The computers used for these simulations are not ordinary desktop machines. They are powerful clusters, often made of hundreds or thousands of linked processors. These machines can handle the enormous number of calculations required to simulate atomic behavior in detail. Some simulations take hours. Others might run for weeks. But when they finish, the data they produce can be more detailed than anything a lab experiment could provide. Visualization is another important part of simulation. Instead of just showing numbers, computers can now create images or even animations of what's happening at the atomic level. These visuals let researchers see what the decay process looks like, how a neutron might drift away from a nucleus, how an unstable particle might split into smaller pieces, or how waves of energy spread through an atomic structure. These images help people who aren't physicists understand the science, and they also help researchers spot patterns that might not be obvious in raw data. Machine learning tools can help make sense of the huge amounts of data that simulations produce. They can also be used to predict outcomes based on past results, finding trends and connections that might take a human months to uncover. Simulations are especially useful for exploring situations that would be impossible to create in a lab. By simulating the conditions inside a neutron star, for example, scientists can make guesses about what happens to matter in such places. Do atoms decay faster? Do new particles appear? Do the rules of decay even stay the same? When designing reactors or studying radioactive waste, researchers need to know how different materials will behave over time. Will a certain isotope remain stable for thousands of years, or will it decay quickly into something else? What kind of radiation will it release, and how far will that radiation travel? Some researchers use them to explore decay processes that may not even exist yet, decay pathways that could reveal new forces or unknown particles. If a simulation suggests that a certain kind of decay should happen under specific conditions, it can guide experiments, helping physicists know where to look and what to measure. But it's important to remember that simulations are only as good as the data that goes into them. They rely on known laws of physics, and if those laws are incomplete or if there's an unknown factor, the simulation won't show the full picture. That's why simulations are usually paired with real-world experiments. The experiments test the predictions of the simulation, and the simulation helps explain the results of the experiments. It's a cycle that keeps pushing science forward. As technology continues to improve, simulations are expected to become even more detailed and more accurate. Quantum computers, for example, could one day simulate atomic systems directly using qubits. These machines might be able to model quantum interactions much more naturally than classical computers, opening up entirely new ways to explore atomic decay and other complex processes. Anomalous decay, when atoms defy expectations. Most atoms that decay follow well-documented processes. Scientists can predict these steps very well using nuclear physics. But every so often, something happens that doesn't fit. A particle may appear where it shouldn't. A decay might happen too quickly or too slowly. A product of decay might have too much energy or not enough. In a Hungarian lab in 2016, researchers were studying the decay of an excited state of beryllium-8. As expected, it was breaking apart into two particles, a process that had been studied many times before. But this time, something extra showed up. The detector caught more particles than it should have, with more energy than the model predicted. At first, it looked like noise, just an error in the data, but the signal kept appearing. This mysterious pattern came to be known as the X17 anomaly, named after the particle scientists believe might be responsible. X17 refers to a possible new particle with a mass around 17 mega-electron volts, which is much lighter than a proton. If it's real, this particle could be a sign of a fifth fundamental force in nature. But the evidence is still debated, and other labs are trying to reproduce the results. Other types of strange decay have been observed in extremely neutron-rich or proton-rich isotopes. These atoms lie far from the stable zone on the chart of Nuclides. They have unbalanced cores, making them prone to exotic behaviors. For instance, some of these isotopes undergo a process known as two-proton emission, where two protons are ejected from the nucleus at the same time. This is not the same as one proton being lost, then another. It's a coordinated event, and it only happens in very specific conditions. Two-proton decay was predicted decades ago, but only recently has it been observed directly, showing just how much we still have to learn. In other cases, strange decay events may come from interactions that involve the neutrino. Neutrinos are nearly massless and interact very weakly with matter. In some rare types of decay, such as neutrinoless double beta decay, 2 neutrons in a nucleus change into protons and release 2 electrons, but no neutrinos. According to standard physics, this shouldn't happen unless the neutrino is its own antiparticle. If neutrinoless double beta decay can be confirmed, it would be a major discovery, hinting at new laws of physics and helping explain why the universe has more matter than antimatter. There are also cases where atoms seem to resist decay longer than expected. In labs that store radioactive materials for long-term study, scientists sometimes find small samples that haven't decayed as quickly as predicted. These differences can be tiny, but even a small deviation is enough to spark questions. Are environmental factors playing a role? Is the decay affected by outside fields or quantum effects we haven't accounted for? Or is there some unknown interaction happening inside the nucleus? In some experiments involving high-energy collisions, detectors have picked up electrons or positrons that don't fit the standard paths. In other situations, a decay might produce gamma rays in a pattern that seems off, as if something unseen is taking some of the energy away. Sometimes, decay processes appear to pause for extremely short periods before resuming. These moments, too short to measure directly, are predicted by quantum theory as fluctuations or temporary stabilizations within the nucleus. While these pauses don't stop decay permanently, they may help explain why some processes happen more slowly than others. The search for understanding in these strange cases often begins with data, huge amounts of it. Particle detectors collect readings from thousands or millions of decay events, and researchers look for patterns that stand out. A slight excess here, an unexpected drop there, these are the clues. And while some of these patterns turn out to be statistical noise or experimental error, others refuse to go away. When that happens, the physics community starts paying close attention. Investigating anomalous decay requires careful calibration of equipment, repeated trials, and lots of cross-checking with other labs. It also requires a deep understanding of the background physics, so that what's truly strange can be separated from what's just uncommon. Scientists use both experimental data and simulations to work out what could be causing the anomaly. If no known interaction or pathway explains it, the next step is to consider whether new theories might be needed. These new theories might include ideas like supersymmetry, where every known particle has a hidden partner. Or they might involve extra dimensions, where particles can disappear into spaces we can't see. Some researchers even suggest that anomalies in decay could be tied to the early universe, traces left behind by forces that shaped the cosmos when it was still young. Whether or not these ideas turn out to be true, they show how strange decay events can open doors to bold new thinking. Anomalous decay doesn't always lead to dramatic discoveries. Many times, what looks like a mystery turns out to have a simple explanation. Perhaps a detector was slightly out of alignment, or a magnetic field interfered with the measurement. But every confirmed anomaly that remains unexplained is a reminder that nature still holds secrets. Hyperexotic atoms and the limits of stability. Hyperexotic atoms exist at the very edge of what's possible in our universe. They are created under extreme conditions, and they last only for the briefest flashes of time. But even in those moments, they can tell us a great deal about how nature works and where the limits might lie. One way these exotic atoms form is by swapping out one of the usual components of an atom with something unexpected. Instead of a normal electron, for example, an atom might trap a muon, a heavier cousin of the electron. A muon behaves like an electron in many ways. It orbits the nucleus. It carries a negative charge, but it's about 200 times heavier. Because of this, it orbits much closer to the nucleus. The entire structure of the atom is pulled tighter, and the interactions between the particles are stronger. These muonic atoms give physicists a rare chance to probe the inner structure of the nucleus because the muon gets so close to it. Some exotic atoms replace electrons with positrons. These atoms are called positronium. In a sense, positronium is not even an atom in the traditional sense. It's a system made of matter and antimatter orbiting each other. It's also incredibly unstable. It only lasts for a fraction of a microsecond before the two particles annihilate each other, turning entirely into energy. And yet, during that tiny lifespan, it still behaves like an atom, with orbitals and energy levels that can be measured and predicted. Then there are super heavy elements that are built by smashing lighter elements together in particle accelerators. Most of the time, the resulting atoms fall apart almost immediately. But sometimes, one of these artificial atoms lasts long enough to be studied. These are the elements at the far end of the periodic table, like element 118, organeson. According to the island of stability theory in nuclear physics, there might be certain combinations of protons and neutrons that form very heavy elements which are unexpectedly stable, more stable than anything around them. The idea is that just as certain numbers of protons and neutrons make stable nuclei in lighter atoms, similar magic numbers might exist for super heavy atoms. If we could find the right combination, we might discover atoms with hundreds of protons that last for minutes, hours, or even longer. So far, though, we've only seen hints of this. Most super heavy atoms created so far decay in milliseconds. There are also hyperexotic atoms that involve strange quarks. In everyday atoms, protons and neutrons are made of up and down quarks. But in high-energy environments, like those in powerful collisions, it's possible to create baryons that contain strange quarks. These particles are heavier, and they interact differently with the rest of the nucleus. If one of these strange baryons becomes part of a nucleus, the whole system is called a hypernucleus. These strange nuclei are extremely rare and don't occur naturally on Earth. They offer a glimpse into a version of matter that might exist in the cores of neutron stars. While antimatter atoms like antihydrogen have been created in labs, they are difficult to study because they disappear quickly on contact with normal matter. To contain them, scientists use complex traps made from magnetic fields, holding the antimatter in place without letting it touch the container walls. For moments at a time, these antihydrogen atoms float in vacuum, just stable enough to be examined with laser light. Beyond antimatter, there are still stranger ideas. Some theories predict particles like magnetic monopoles, particles with only one magnetic pole instead of the usual north-south pair. If such a particle were found and bound into an atomic structure, it would create an entirely new kind of atom. Others imagine atoms formed with dark matter particles, which would be invisible except through gravitational effects. These remain speculative, but they're part of the ongoing attempt to understand what matter is truly made of and how flexible the atomic model might be under the right conditions. In laboratories, researchers continue to push the limits of what counts as an atom. They adjust the balance between protons and neutrons and explore how external conditions, like high pressure or strong magnetic fields, can keep atoms stable even when their natural lifetimes are short. Because many of these atoms are so short-lived, much of the study depends on fast detectors and precise timing systems. The entire lifespan of a hyperexotic atom might be measured in nanoseconds or less. Scientists design experiments that trigger, detect, and analyze these events almost instantly, pulling information from bursts of data that happen faster than the blink of an eye. As tools improve, the frontier of atomic research keeps moving outward. New accelerators, better magnetic traps, and advanced computing all contribute to the search. In some ways, it's like exploring a coastline with waves constantly eroding and reshaping it. Each discovery of a new exotic atom redraws the edge of the map, hinting at possibilities just beyond reach. Conservation of information. Imagine watching an unstable atom decay. We can measure the energy, the mass, the speed, but the atom before the decay held more than just numbers. It had a location, a spin, a unique history of how it formed. That history doesn't leave a physical mark in the decay products, and yet, according to some interpretations, it shouldn't just vanish. The tension between this belief and what we actually observe grows sharper when we look at the most extreme environments in the universe. A black hole may grow in mass or change its spin, but the fine details of what fell in, the structure of atoms, molecules, or even complex matter, appear to be gone. This leads to the black hole information paradox. If an atom falls into a black hole and is crushed out of existence, is the information that described it lost forever? If that's true, it clashes with one of the most basic rules of quantum theory, that the evolution of systems is reversible, that the information about the past must always be encoded in the present. This puzzle has pushed physicists to think harder about what information means. In physical terms, information refers to the arrangement of a system. If two atoms have the same number of protons and neutrons, but their particles are moving in slightly different ways, then they hold different information. So when an atom decays, the question is not just where its parts go, but whether those parts carry enough detail to reconstruct what once was. Most of the time, this isn't practical. A single electron from a radioactive decay doesn't seem to tell us much about the original atom. But in theory, if we had perfect knowledge of the outgoing particles and their relationships, we might be able to trace the original state. The information isn't lost, it's scattered. Some researchers suggest that even the vacuum of space holds the potential to preserve information. When a particle passes through or decays nearby, its influence might alter this structure just enough to record that it happened. Not like a notebook, but like a footprint in soft soil that slowly fades, yet never quite vanishes. There are also ideas involving holography, the theory that suggests all the information in a volume of space might be encoded on its surface. In this view, everything happening inside a region, including the decay of atoms or the fall of matter into a black hole, could be described by patterns on a surrounding surface. If this is true, then even the most destructive processes might not erase information, but only move it to a different layer of reality. The search for where this information goes affects how we understand time, causality, and even what it means for something to exist. If information can never be lost, then everything that has ever happened still exists in some form, embedded in the universe. Some research groups are testing how entangled particles behave after one is lost or scattered. Others are watching black hole analogues in labs, using fluids or light to mimic how matter and energy behave near an event horizon. These models don't prove anything yet, but they suggest that nature might keep better records than we had previously thought. Future directions, unlocking the mysteries of atomic transformation. In laboratories around the world, scientists are building machines that can watch atoms at the very moment they begin to change. One of the most promising directions is the use of ultra-cold environments, temperatures just above absolute zero, where atomic motion slows down enough that transitions can be observed with stunning clarity. In these conditions, even the earliest signs of decay can be captured, sometimes down to the changes in energy levels before particles are released. A few rare isotopes have shown decay signatures that can't be fully explained by current models. Tracking these anomalies is becoming a major focus. If patterns are found, they could point to entirely new physics, possibly revealing things like unknown interactions or hidden dimensions. New types of detectors are also coming online. These are built to look for rare decay events that might only happen once in a billion or trillion attempts. One of the most sought-after signals is from a neutrinoless double beta decay. Capturing even a single confirmed event would be a breakthrough. Quantum computing could become a major tool in this space. If the technology continues to advance, future scientists could run experiments testing decay pathways, particle behavior, and even exploring hypothetical conditions like curved spacetime or altered field strengths. Could we one day slow down or speed up decay in controlled environments? Could decay processes be harnessed for precise nanotechnology or medicine? There are already treatments in cancer that use targeted radioactive atoms to destroy tumors. But what if those atoms could be tuned more precisely, decaying at just the right time and place? These questions are only beginning to be asked. Then there's the question of teaching machines to recognize patterns that we miss. AI doesn't need to know what it's looking for. It can simply flag outliers and unusual results. If this approach continues to grow, it might lead to discoveries that human researchers wouldn't even think to search for. Synthetic atoms. Engineering immortality in matter. Scientists have created atoms of new elements like oganesson and flerovium, elements that don't exist naturally on Earth. Each one adds to our knowledge of how atomic structure works. More importantly, these artificial atoms show us that atomic life can be extended, altered, or even created from scratch. Could we design atoms that don't decay at all? In nature, there are already atoms considered stable for practical purposes: hydrogen, helium, carbon. They hold together for billions of years. Some scientists are studying these naturally long-lived atoms to understand what gives them such resilience. Is it their size, the number of protons and neutrons, the energy balance inside their cores? Once we learn what makes an atom stable, the next step is figuring out how to build one that's even more so. But the real challenge isn't just building a stable atom, it's controlling the environment that surrounds it. Atoms decay when they reach a point of imbalance. Radiation escapes, energy leaks out. Sometimes it's a neutron slipping away or a sudden shift in the atomic core. But what if we could contain that energy? What if we could build a shell around the atom, a field, a structure, a shield that keeps it from falling apart? This leads to research in atomic traps, electromagnetic fields, and even quantum feedback systems. These setups use finely tuned energy patterns to hold atoms in place, suspending them in ways that might reduce or delay decay. While current technology doesn't yet allow full prevention, early experiments show that atomic behavior can be slowed, adjusted, or redirected. The more precise our tools become, the more options we have for guiding an atom's life, rather than simply observing its death. Another avenue being explored is repair. In biology, cells can sometimes fix themselves when damaged. Could atoms do the same with help? If a neutron breaks loose, could we insert another? If energy starts to shift, could we stabilize it before it collapses? Techniques like neutron capture and isotope transformation already hint at this idea. In reactors, atoms are sometimes transformed in predictable ways, absorbing or releasing particles in a controlled environment. Extending this control into full repair might be far away, but it's not unthinkable. Quantum computing and nanotechnology both require precise control over individual atoms or electrons. The advances made here, better ways to trap atoms, read their states, move particles without disturbing them, are laying the groundwork for deeper atomic engineering. As machines grow smaller and faster, we may reach a point where altering atoms becomes not just possible, but routine. Synthetic atoms would no longer be strange exceptions. They'd be tools used in medicine, computing, energy, or even construction. Could we design atoms with completely new behaviors? Atoms that store energy in new ways, or that emit specific forms of radiation on command? Custom atoms for specific jobs, impossible to decay, immune to time. Such ideas challenge our assumptions about nature's rules. They ask whether we're forever bound to the elements the universe began with, or whether we can rewrite the atomic language itself. What are the risks of matter that doesn't break down? In nature, decay plays a role in recycling materials. It helps stars evolve, powers life processes, even warms the Earth's core. If we build matter that doesn't decay, we might need new systems to balance its effects. Perhaps these atoms would have limited use, applied only where decay is dangerous, such as space travel, long-term power storage, or highly sensitive data environments. Some researchers are already testing how synthetic atoms behave in extreme environments. High-energy plasmas, magnetic fields, and vacuum chambers are all used to see how long artificial atoms can last under stress. These environments act as testing grounds for stability. The goal is not just to create atoms that survive longer, but to understand what truly keeps them together. Some scientists believe that immortality, in any form, is less about lasting forever and more about controlling transformation. The atom doesn't have to live forever. It just needs to change in ways we can guide, understand, and perhaps reverse. Already we see atoms used in ways nature never intended, guiding lasers, forming superconductors, storing quantum information. The future may hold even more. Atoms that adapt, respond, and evolve. Matter that doesn't merely exist, but that acts in deliberate ways, built by human hands for specific futures. Artificial black holes, testing the limits of the atom. When you want to explore the most extreme environments possible, there's only one force in the universe powerful enough to fully test the resilience of matter: the black hole. But what if we didn't have to wait for a distant cosmic event to study this process? What if we could make a version of a black hole here on Earth? Not to destroy worlds, but to investigate the deepest questions of atomic disintegration. That's where the idea of artificial black holes enters the picture. These wouldn't be massive enough to swallow stars or bend galaxies. Instead, they are small, controlled simulations of black hole conditions created inside labs through high-energy experiments. These artificial black holes, often called micro-black holes or analog black holes, give researchers a chance to study how atoms behave when exposed to the kinds of forces usually found only near the edge of a singularity. Creating a micro-black hole is not a simple task. The theories behind it suggest that if two particles collide with enough energy, they might briefly compress space so tightly that a miniature black hole is formed. This would be far smaller than a proton and exist for an incredibly short time before evaporating. In large particle accelerators like the LHC, collisions occur at near-light speeds. While no artificial black holes have yet been confirmed from these events, the possibility remains, especially as energies increase and new detection methods are developed. If one could create such a black hole safely and observe it closely, it might reveal what happens to atoms under the most extreme gravitational forces imaginable. The idea is not to watch the atom in isolation, but to expose it to a field that twists, bends, and compresses space itself. In this warped environment, atoms wouldn't just decay, they might be torn apart entirely. Protons could be pulled out of their shells, electrons stripped from their orbits. Even the very particles inside the nucleus might begin to unravel under the crushing pull. This level of atomic breakdown is unlike anything seen in normal conditions. What we would be witnessing is not just atomic decay, but complete disintegration. This could help researchers better understand what happens inside real black holes, where even fundamental forces might behave differently than they do elsewhere in the universe. One of the most fascinating aspects of these experiments would be watching what, if anything, comes out of such destruction. In nature, black holes don't just consume, they also radiate. Stephen Hawking once proposed that black holes emit energy over time, a process known as Hawking radiation. If artificial black holes emit any kind of energy during their brief lives, they could offer a new window into how matter transforms at its very end. This radiation might carry the last traces of the atom that once was, offering clues about its structure, its energy, and possibly even its history. The study of these radiation patterns could be especially important for understanding whether information is truly lost inside a black hole. The energy and particles released during evaporation could be analyzed for patterns, correlations, or unexpected features that hint at some form of memory lingering in the wreckage of matter. To simulate these events without building actual black holes, scientists have also begun using analog systems. These include setups like sound waves in fluids or light waves in special optical materials, which behave in ways that mathematically mirror the effects of gravity in a black hole. These systems don't use gravity, but they mimic the same rules that black holes follow, allowing researchers to study black hole-like behavior in more controllable environments. When particles pass through these setups, their paths, speeds, and energy levels shift in ways that can be tracked and studied in detail. Inside these analog experiments, researchers can send atoms, or at least their quantum states, into artificial horizons. These horizons act like the edge of a black hole, trapping certain parts of the system while allowing others to escape. The idea is to observe what happens to particles on both sides. Does the information split? Is energy conserved? Do the atoms die in a way that matches what black hole physics would predict? These experiments are being used to answer some of the most difficult questions in both quantum mechanics and general relativity, especially where the two fields overlap. Perhaps more surprisingly, some theories suggest that under certain conditions, black holes might even be capable of forming new matter. If virtual particles and energy fields behave in particular ways near the edge of a black hole, they could combine to create new particles, possibly even new atoms. An atom might be pulled apart completely, but the energy and particles released in the process could later recombine into new forms of matter. Even if this recombination doesn't happen inside the black hole, it might occur afterward, as the field collapses and the energy disperses. This level of experimentation is still in its early stages. No one has built a working artificial black hole capable of such effects yet, but the tools are getting better. And with every new step forward, scientists get closer to building experiments that test the atom not just in theory, but against the universe's most unforgiving forces. Atomic demise across the multiverse. The idea of the multiverse suggests that our universe is just one of many. Some of these universes might be nearly identical to ours, with only slight variations in physical constants, like a slightly stronger force of gravity, or a small difference in the strength of the electromagnetic field. Others could be wildly different, where time behaves strangely, particles don't follow the same rules, or atoms themselves can't form at all. Within this massive range of possibilities, the process of atomic destruction could take on entirely new forms. In our universe, the decay of atoms often follows predictable paths. The laws of quantum mechanics and thermodynamics keep these events ordered, and we can model them with confidence. But if you move into a universe where those laws are changed, everything from the atom's stability to the way it decays might be altered beyond recognition. Consider a universe where the strong nuclear force is weaker than it is here. In such a reality, atoms as we know them might not survive long at all. Even the most basic elements like hydrogen could fall apart within moments. Matter wouldn't have the same permanence. Planets, stars, or even molecules would never form because their building blocks would crumble too quickly. The idea of atomic death wouldn't be an isolated event. It would be a universal feature of existence, happening continuously at every scale. On the other hand, imagine a universe where the strong nuclear force is much stronger. In that case, atoms could become so tightly bound that decay becomes extremely rare or impossible. Radioactive materials might remain unchanged for eons. Energy release from decay might not occur naturally. In a world like this, the concept of decay would carry a very different meaning. Instead of being a common process that fuels stars and powers nuclear reactions, it might be a rare phenomenon triggered only under extreme artificial conditions. Other universes might not use the same particle layout as ours. Instead of protons, neutrons, and electrons, there might be entirely different fundamental particles governed by unfamiliar forces. In such a place, atoms might exist in entirely different shapes and structures, if they exist at all. An atom might dissolve not because of internal instability, but due to external interactions with fields or particles we don't have here. Some physicists also imagine universes with more than 3 spatial dimensions. In our world, atoms exist in 3D, and the way they bind together is based on how particles interact in that limited space. If a universe had 4 or more dimensions, the geometry of atomic structures would change. Electrons might spiral in different paths, or not orbit at all. Decay could happen more rapidly, or not at all, depending on how the forces stretch across space. There's also the possibility of universes where time itself flows differently. In some theoretical models, other universes might have a different time structure, non-linear, cyclical, or even bidirectional. If atoms existed in such a place, their decay might not be a one-way journey. Instead of dissolving permanently, atoms might disintegrate and then reassemble, like a natural rewind button built into the fabric of time. Atomic death in such universes could be temporary or reversible. A decayed atom might return to its original form as time loops back or as causality flows in a different direction. In these worlds, destruction wouldn't be an endpoint. It would be part of an ongoing cycle where the same particles come apart and come back together in an endless rhythm. In more speculative versions of the multiverse, there might be places where quantum mechanics itself doesn't exist in the same way. Maybe probabilities don't rule particle behavior. Maybe everything is deterministic, or the universe is governed by an entirely different set of rules. In such a place, decay might happen in ways that don't involve energy release. The whole concept of an unstable atom might not apply. Some researchers also entertain the idea of baby universes, small, newly formed regions of spacetime that branch off from a parent universe. If a high-energy event, like atomic collapse, could somehow trigger the formation of such a universe, it's possible that the death of an atom in one universe could be the birth of a new one in another. In this view, atomic demise could have cosmic consequences, potentially acting as the seed for new universes, each with their own unique physics and particles. From a research standpoint, exploring these questions is nearly impossible with current technology. We can't observe other universes directly, and we don't yet have a way to test whether alternative physical laws actually exist outside our own. But theoretical physicists can still simulate these ideas using mathematical models and powerful computers. They create virtual atoms under different rules, adjusting the constants to see how they behave. These simulations can show how small changes in fundamental forces lead to completely different outcomes, not just in atomic stability, but in how matter forms and dissolves. Some of the most advanced models use what's called a parameter sweep, where a computer runs through thousands of different values for physical constants like gravity or the strength of the weak nuclear force. By observing how atoms form or fail to form in each scenario, researchers can get a sense of which combinations allow for atomic stability and which lead to rapid decay or chaos. This helps map out what's sometimes called the life-friendly zone of the multiverse, the range of universes where atoms not only survive, but thrive. If matter is shaped entirely by the rules of its environment, then the identity of the atom isn't fixed, it's conditional. Its life, its death, and its entire history are all bound to the laws of its universe. Change the laws and you change the atom. Perhaps even more deeply, you change what it means for an atom to die. The science of atomic memory. Atoms are not just tiny billiard balls bouncing around in empty space. They exist in defined states, and these states, energy levels, spin directions, quantum properties, hold information. When an atom is excited, absorbs energy, or decays, it transitions between these states. This process follows strict rules, driven by the fundamental forces of nature. These rules and patterns are precise, and the outcomes can be predicted. In this sense, the history of an atom is written into the structure it leaves behind. A radioactive atom's decay products have specific energies and momenta that match the rules of conservation. They show that something specific happened, not something random. The daughter atom remembers the parent in its configuration. It holds onto a part of the story. Quantum systems are not only defined by their current state, but also by how they got there. This path dependence is sometimes subtle, but it's real. A system that has been disturbed or measured carries that history forward in the way it behaves. Experiments with entangled particles make this clearer. When two particles are entangled, if one decays, that information is transferred. It's preserved in the correlations between the two. This isn't memory in the usual sense, but it's a kind of a quantum record. The same logic applies to atoms interacting with light. When an atom absorbs a photon, its energy level changes. When it emits that photon, it returns to a lower state, but the photon it emits carries information about the atom. Its wavelength, direction, and timing depend on the exact structure of the atom and the energy difference between its states. In astrophysics, this principle helps scientists study distant stars and galaxies. In recent years, physicists have been exploring even deeper ideas about information and memory at the atomic level. One area of interest involves decoherence, the process by which a quantum system loses its quantum nature and begins to behave classically. Decoherence is a kind of forgetting, where the delicate superposition of states becomes entangled with the environment and fades into noise. But in this noise, information may still be present. It's just hidden, scattered through the many interactions that followed. The system no longer holds a clear memory, but the environment around it might. This raises the possibility that memory is not always local. When an atom decays, the particles and energy released interact with nearby particles, with fields, with space itself. Over time, this information spreads, becoming part of the larger system. The original drop is gone, but the waves remain. Atomic memory might not vanish, it might dissolve into the universe. This touches on another idea, reconstructibility. Given enough data and enough understanding, it might be possible to reconstruct the state of a decayed atom. In principle, if every particle and field that interacted with the atom is known, and every law that governed those interactions is understood, then the past could be unraveled. Such reconstruction is far beyond our current abilities. The number of variables involved is astronomical, and the measurements required would be more precise than anything we can currently achieve. But as technology improves, researchers are beginning to simulate small systems with remarkable accuracy. Using ultra-cold atoms, scientists can track individual particles through chains of interactions. They can observe how information flows and decays, how structure forms and breaks apart. Is memory simply stored information? Or is it something more? An active relationship between past and future, a structure that resists time's pull. If atomic states hold information that can, in theory, be recovered, then atoms may not forget. Even after destruction, even after change, they may leave behind a mark, something that says, "I was here." Post-decay, the state of the world beyond the atom. Imagine waking up in a place where nothing moves, nothing shines, and nothing grows. A place where every star has burned out, every planet has turned cold, and every atom, once the building block of everything, has finally broken apart. This is not just the end of a world or a galaxy. This is what it might be like to find yourself in the universe after everything has decayed. After heat death. After time, energy, and matter have stretched themselves to the edge of meaning. At first glance, there's only darkness. Not the kind of darkness we see on a moonless night, where stars still blink in the distance. This darkness has no texture, no depth. It does not invite exploration. It simply is. The background temperature is barely above absolute zero. There are no suns to warm your face, no echoes of a planet underfoot, no sound. Even sound needs matter to travel through, and in this place there is nearly none left. Long ago, before this moment, the universe was filled with motion. Galaxies collided, stars exploded, atoms vibrated. But in the wake of heat death, those days are over. The forces that once held atoms together have unraveled over eons. Protons have likely decayed into lighter particles or radiation. Neutrons, no longer stable on their own, faded even sooner. Electrons, without anything to orbit, drifted quietly into nothingness or were absorbed by black holes that have since evaporated themselves away. What remains is a kind of dust, not in the usual sense, not like the dust that floats in a sunbeam. This dust is ghostly. It's the residue of a universe that has used up its ability to do anything useful. All the gradients are gone. No pressure differences, no energy imbalances, and without those, nothing can happen. Nothing can build. Nothing can break. Everything that could happen has happened. Every system has run down. And because energy has spread itself out as evenly as it can, there are no more hotspots, no more cool pockets, no more sparks. This is the state of maximum entropy. And strangely enough, it might be the quietest state that nature can achieve. If you could somehow stand in this world, you would not feel gravity pulling you down. The great cosmic structures that once shaped space massive galaxies and black holes, have long since vanished. Gravity is still a property of space, but there's almost nothing left to bend it. Space no longer ripples with gravitational waves from distant cataclysms. Those ripples have faded into the endless stretch, stretched thin and quiet, like a whisper too far to hear. Time still exists, but it no longer matters in the way it once did. There are no clocks to measure its passing, no events to mark its rhythm. In earlier times, stars aged, atoms decayed, and black holes shrank. These were ways that the universe kept time, through change, through process. But in a world where nothing changes, time becomes just another empty dimension, one that stretches forward but holds no difference from one moment to the next. Particles still exist, but they are lonely and rare. Photons still roam through the void, but they are so low in energy, so stretched out by the expansion of space, that they cannot interact with anything. If a photon travels forever and never strikes anything, does it still count as light? These ancient photons carry the memory of an earlier universe, but they can no longer deliver their message. Over billions upon billions of years, space expanded at such a rate that even particles that once shared a common origin are now beyond reach of each other. The distances are so vast that light, the fastest thing in the universe, cannot cross the gaps. In this way, the universe hasn't just faded. It has shattered into islands of isolation, each one cut off from the others by the sheer immensity of nothing. To teleport into this future is to enter a universe where the concept of here has lost all meaning. The universe began in chaos, a hot, dense flash of energy that exploded outward in all directions. From that storm, atoms formed, then stars, then galaxies, then life. In the end, it doesn't collapse back to a violent singularity. It does not rage. It rests. Every atom that ever was, every thought ever thought, every life ever lived, they all led to this moment of perfect stillness, the last page of a very long story. If we ask what happens after heat death, the truth is nothing. That's the point. Heat death is the name we give to the idea that the universe eventually reaches a state where no more work can be done, where every source of potential energy has been used up, where even atomic and subatomic decay has finished. There are no new beginnings after this, no cycles of rebirth unless something beyond known physics intervenes. Some have speculated that quantum events might still flicker in the darkness, producing rare particles or even small bursts of energy. But these are not enough to build stars or planets. They are isolated sparks in a sea too vast and too cold to care. And yet, this image is not entirely bleak. The idea that every particle in the universe followed a path that led to this moment, that every decay, every collision, every transformation was part of a single arc, spanning trillions of years, gives a kind of quiet beauty to the stillness. The chaos has passed, the journey is complete, and in the end, the universe gets to rest. What other topics would you like an exhaustive investigation on? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.